Let's move on to Chapter 9, which is on discrete time Fourier analysis. So we looked at Fourier analysis of continuous time systems. If you'll remember, we started with continuous time Fourier series of periodic signals, and then moved on to the Fourier transform. We'll take a similar approach here, starting with the discrete time Fourier series, which I'll abbreviate DTFS. A periodic sequence is one that satisfies the definition x of n is equal to x of n plus n0, where n0 is the period of the sequence. The sequence is said to have a fundamental frequency of omega 0, which is 2 pi over n0, and its exponential Fourier series consists of terms of the form e to the j 0n. Of course, this is just 1 e to the plus or minus j omega 0n, and then e to the plus minus j 2 omega 0n. So multiples then of omega 0, which are said to be the harmonics. Unlike the continuous time exponential, the discrete time exponentials are periodic in little n with period n0, and that's easy to prove. So for example, take e to the j k omega 0 n plus n0, and we can write that as e to the j k omega 0 n plus omega 0 n0, or e to the j k omega 0 n plus 2 pi, because of our definition of omega 0 as 2 pi over n0. This product of omega 0 and n0 has got to be equal to 2 pi. But this is then just e to the j k omega 0 n. Again, this is a fundamental difference between our discrete time signals and our continuous time signals with regard to this exponential sequence. It means that the k plus n0th harmonic is identical to the kth harmonic. So there are only n0 harmonics for a periodic discrete time signal, whereas for a continuous time signal there are an infinite number of harmonics, and these harmonics are separated by omega 0 equal to 2 pi over n0. So in the frequencies start at 0 and go up almost to 2 pi. The Fourier series is given by, the discrete time Fourier series is in the exponential form, which is the only one we'll deal with. Again, it's not an infinite summation, since there are only n0 harmonics. So our sum runs over n0 terms, going from 0 to n0 minus 1. We have the Fourier series coefficients, which we'll indicate by capital D with a subscript r, and then times our harmonic exponential terms, e to the j r omega 0 n, where our Fourier series coefficients are equal to 1 over n0, the sum from n equals 0 to n0 minus 1 times our periodic sequence x of n e to the minus j r omega 0 n. Okay, and again, omega 0, our fundamental frequency, is 2 pi over n0 here. The dr are complex, so we can write the dr as being equal to, in exponential form, as a magnitude e to the j angle of dr. Okay, this is the most useful representation. The amplitude and phase spectra are plots of the amplitude of dr and the phase angle of dr versus omega. I should also note that the dr are periodic as well. With period n0, again, as are our original discrete time sequence and our exponential terms. So the summations in the Fourier series can actually be over any n0 interval because of the periodicity of the Fourier series coefficients. So I'll write that like this. So it doesn't necessarily have to be from 0 to n0 minus 1 of dr e to the j r omega 0 n. And then similarly we can compute the dr by actually summing over any period of x of n and e to the minus j r omega 0 n. A couple of notes on the discrete time Fourier series. Again, just remember, not all discrete time trig functions are periodic, unlike their continuous time counterparts. So, for example, x of n is equal to cosine of omega n. This is a trigonometric sequence. It's periodic only if we can find an n0 such that, where n0 is an integer, such that xn plus n0, which would be cosine omega n plus omega n0, is equal to cosine omega n. So this is periodic only if this omega n0 term is an integer multiple of 2 pi. So omega n0 is equal to some integer m times 2 pi, or the implication is only if omega over 2 pi is equal to a ratio of 2 integers, which requires that typically omega is going to be some integer multiple of pi. So it's periodic only if omega over 2 pi is rational. And if so, the period in that case is n0 equal to 2 pi, some integer multiple times 2 pi over omega. So just a couple of quick examples. So for example, cosine of 0.2 pi n is periodic. Since 0.2 pi over 2 pi is equal to 1/10, which is a rational fraction of integers, and the corresponding period is 10. Cosine of 0.3 pi n is also periodic, since 0.3 pi over 2 pi can be written as 3/20, and so the corresponding period is 20. But on the other hand, cosine, for example, 0.2 pi n is not periodic, since we can't write 0.2 over 2 pi as a ratio of integers. Recall, of course, that only periodic signals have Fourier series representations. Another note is that, if you remember our discussion about fundamental frequency and apparent frequency, all discrete time trigonometric functions have equivalent frequencies between minus pi and pi, or equivalently between 0 and 2 pi, but we'll use minus pi and pi as our fundamental frequency interval. So for example, x of n is equal to cosine of 4.5 pi n plus theta. We can rewrite that as cosine of 0.5 pi n plus 4 pi n plus theta, or again equivalently as cosine of 0.5 pi n plus theta. So these two sequences are indistinguishable, and we'd say that the apparent frequency of this sinusoid is actually 0.5 pi. Similarly, for another example, cosine of 3.5 pi n plus theta, we can write as cosine of minus 0.5 pi n plus 4 pi n plus theta, which is cosine of minus 0.5 pi n plus theta, and say that this has an equivalent frequency of 0.5 pi n. If you recall, we can also say that that was equal to cosine of 0.5 pi n minus theta, just by taking the negative of the argument. So in the next video, we'll look at a couple of example problems of computing Fourier series.